The objective of this video is to finish developing our rigid body model to also include the impact of cross-axis coupling that is caused by gyroscopic forces. So at the end of this video, we will have a single complete model in what's referred to as the COGs coordinates, the center of gravity coordinates. But let's start by reviewing the system that we are working with. So I've sketched in these diagrams the system that we considered in our previous video, which is our 4-degree of freedom system. And so we again have magnetic bearings or bearingless motors on two ends of a shaft, which are able to produce X and Y forces on those ends. And we have these state variables of X0, beta, Y0, and alpha. So picking up from there, we can note that gyroscopic forces are actually torques. These are torques that arise when our shaft is rotating about the z-axis. So if this is our motor shaft and we've got our motor spinning, suddenly we will get these torques which cause cross-coupling between the y and x axes. And so I'm highlighting the new term that has been added to our differential equation. The rest of this differential equation should be familiar to you from our previous video. If it is not, please go back and review that. So this new term, this tau beta omega and tau alpha omega, is as follows. Tau beta omega is equal to our moment of inertia about the motor's axis times the rotational speed of the motor times alpha dot. Tau alpha omega is equal to the negative of our rotor's moment of inertia, the motor's moment of inertia, times its rotational speed times beta squared. So I'm noting that omega is the rotational speed of the shaft as being the time derivative of theta, where theta is the rotation about the z-axis. So that is the speed of our motor. And again, pay attention to the sign change here, that you've got a negative here and a positive up here. So gyroscopic forces tend to be stabilizing forces. They tend to kind of stabilize your shaft. When you're familiar with playing with gyroscopes as kids, if you get a gyroscope spinning fast enough, it can kind of behave like an inverted pendulum and hold itself upright. In a magnetic bearing system, they cause your poles to move around on you, and they can cause an otherwise stable control implementation to be unstable. And so it's important for systems that go at very high speeds or have significant inertia that we model these gyroscopic forces and compensate for them. And so we're actually able to use the same control paradigm that we've been developing over the last several videos if we properly compensate for these for these gyroscopic forces. And we can do this with a feed forward. So writing our differential equation from our previous video and then modifying it by our new gyroscopic torque, we get the following. And you can see that on the left side, we have our original differential equation that we previously talked about. And so we can design our controllers in the same way to control our state variables here of beta and alpha. And then on the right side, we can just feed forward these terms to decouple their cross-coupling. So if we do this, a control structure might look like the following. And so we end up with a control structure like this. So you can see we're feed forwarding our alpha dot dependence up here and our beta dot dependence over here. And then down on the right side where we have our physical system to the right of this. So on the right we have our physical system, and on the left we have our decoupled controller. You can see that in our physical system we are modeling our dependence on alpha and beta between the two systems over here. So the red lines indicate the signals that have been the modifications to this block diagram from what we previously had. So the red lines indicate the modifications to this diagram from what we had when we did not consider gyroscopic forces. Next, we're going to take our complete differential equation model, that is including the gyroscopic forces, and write this out in matrix form. And the coordinates that we have picked are referred to as the center of gravity coordinates. You can pick other coordinates instead, but this formulation is referred to as the center of gravity coordinate formulation. The formulation looks like the following. We have this q vector, which are our state variables. We have this fc vector, which are the inputs that we provide to our mechanical system. That is the forces in each actuator, the x and y forces of each actuator. And we have our outputs, which are what our sensors measure, x1, x2, y1, and y2. And then we have these matrices, which we're now going to populate. The matrix M is referred to as a mass matrix. The matrix G is referred to as a gyroscopic matrix because it models the gyroscopic physics. And the matrix K is referred to as a stiffness matrix. So all of this is a canonical form. You're going to come across this in papers and in textbooks, and so I want to summarize it now in terms of a magnetically levitated shaft. So we will now write out our matrix expressions, but first, before we do that, I want to have you recall the differential equations that we were putting into matrix forms. So these are our four differential equations. This is just a review of what we've already written out. I've just taken, for example, these differential equations right here, and I've moved this term and this term over to the left side. So these are all the equations that you're already familiar with. We've derived them in the last several videos. I've just moved some terms over to the left side, so that's conducive for writing our matrix form out like this. And now I'm going to write out the matrix form of these equations. So we've started with this top equation here, and we've noticed that in terms of double derivatives, it only depends on a beta dot dot. So we've got our j beta times beta dot dot, and then 0 is going across the matrix. Next, we have a term that depends on alpha dot, and since our coordinate is a negative alpha dot, that just becomes, this negative quantity becomes a positive quantity because it's multiplied by the negative alpha dot. And next, we're looking for terms that don't depend on a derivative, which we have right here. And so you see we have a negative r delta squared times k delta, which we have right here, and 0 is the rest of the way across. And finally, on the right-hand side, we have a negative r delta times fcx1, so we have that here. And then r delta times fcx2 is positive, which we have right here. And now I'll populate the remaining rows of this matrix formulation. And so you can see our complete formulation. Next, we're going to write out this term over here. And to do that, you need to recall how we map x1, x2, y1, and y2 to our state variables. We did that with the following relation in our previous video, and we came up with this dependence on alpha and beta by using a small angle approximation. So now I'll write out the matrix expression of this equation. Which we now have here. So this represents a canonical form, like I was saying, and you can use these matrices. You can study the form and shape of these matrices and properties of these matrices to understand things like the stability of the system, the observability of the system. There's a rich body of controls and linear and system theory literature out there that will help you design controllers to act on this system and to study this system. And this is the standard format that you will see magnetic bearing papers published in when they're discussing the control of a centralized implementation, a centralized control implementation. So to review, this video has continued developing the rigid body model to include the cross-axis coupling due to gyroscopic forces. We developed our differential equations to model this. We sketched out the block diagram of our physical system attached to our controller. And this should say decoupled controller. And then we put the system into the standard center of gravity coordinate formulation, which is a series of matrices, a set of linear equations, coupled linear equations in a matrix representation.